So I'm starting out with a proof. It says prove that change in momentum equals mass times velocity change. First of all, we have to define what we mean by change in. There is a chance you might know this already. Does anybody know what's change in anything in physics? It's always something minus something. Does anybody know what those two somethings are? I snuck it in my Science 9 if you had me for Science 9, but I didn't do a big song and dance. I don't think I had anybody here for Science 9. I did not. Change in anything is always final minus initial. You know what? It's worth highlighting that or putting a star next to it or something, because I am going to come back on that fairly often. What's change in anything? Final minus initial. So you know what the change in velocity is? It's the final velocity minus the initial velocity. Do you know what the change in voltage is? It's the final voltage minus the initial voltage. You know what the change in anything? It's always final minus initial. Okay. It says prove that change in momentum equals mass times velocity change. There's a symbol for change in. Yeah, I know where I'm going with this. Does anybody remember what the symbol? Does anybody know? Yeah. Delta is the fancy schmancy term, but yeah, triangle. So you ready? We want to prove that change in momentum equals mass times change in velocity. Because I'm trying to prove it, I'll put a little question mark above the equal sign. Are they the same? Okay. What's change in anything? Thank you for getting the hint. So I'm going to break this change in velocity. I'm going to break it into mass bracket V final minus V initial. You okay with that, Rowan? No, nothing spectacular there. And then I'm going to pull out some Math 8 or Math 9, what Mr. Rocca calls front door bomber. I've never understood. I'm going to do that, get rid of brackets. And when I do that, I get MV final minus MV initial. Oh, as a physics concept, what is mass times velocity the same as? Now you're knowing why I did that little rant at the beginning of the lesson. I said momentum is what times what, and you all said mass times velocity. So what's mass times velocity? So what's mass times velocity final? Momentum and mass times velocity initial is initial momentum. I just saw a couple of students' eyes go, oh, I see where he is. Jabber, what's final minus initial the same as? Which is what I was trying to prove. I was trying to prove that mass times change in velocity is the same as change in momentum. I started on the right side and ended up with the left side. So these are interchangeable. And why did I start with that? Impulse is defined as change in momentum. So in Star Trek, when they were talking about the impulse engines, the mass of the starship wasn't changing, its velocity was changing. Yeah, that's what they were doing. They were changing the ship's velocity. Those are called impulse engines. They got the physics right. Their method was nonsense, but the physics was right at least. What's impulse the same as? Change in momentum. What's another word for impulse? Change in momentum. What's another phrase for impulse? Everybody. And what's change in anything? Okay, do you see that little link of chains? I am going to ask you very often. I'll talk about impulse. And what you need to realize, Evan, is, oh, he really means change in momentum, which is going to be the final momentum minus the initial momentum. That's one way to find impulse. Find the final momentum, it'll be V final, and hopefully by now you're comfortable figuring out what's V final and what's V initial. We've done a bunch of that from before the break. Find the initial velocity, it's going to be MV final minus MV initial. There's another way to calculate it. This is the actual impulse equation. It says, fill in the steps below to find the impulse equation. We're going to start with Newton's second law, F equals ma, and we're going to get the a by itself. If F equals ma, what does a equal? Then we're going to take Vf equals Vi plus At and get the a by itself. Ooh, that was from before Christmas. But we can do that. What's going to drop down like a domino? The Vf. And then who remembers, how would we get the a by itself from Vf minus Vi? More specific, can you give me the whole thing? A equals Vf minus Vi. Good. Evan, can you read this to me again? A equals... Jabber, can you read this to me? A equals... So A equals F over M, and A equals Vf minus Vi over T. So this equals A, and this equals A. Well, then they must equal each other, because they both equal A. That's what we're going to use to derive a new equation. We're going to say, okay, F over M equals Vf minus Vi over T. This has got fractions. Let's get rid of the fractions. I'm going to cross multiply. I'm going to multiply the t up to here. I'm going to multiply the m up to here. I think, yeah, cross multiply is on the next page. So we're going to get this. F times t equals m v final minus m v initial. Oh, sorry, hang on, I went too fast. It's going to be m bracket v final minus v initial is technically what I think I should have written, but I foiled it. I multiplied it out in my head. But here's what I want you to notice. My final step, I said, substitute the result from the beginning of the lesson. What is mv final minus mv initial the same as? What was the very, 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 very first thing I was trying to prove? Change in, looking for it begins letter M, or a single word that starts with letter I. A single word that... This is the impulse equation. It says this. If you want to find the impulse, another word for which is change in. If you want to find the impulse, another word for which is change in. Okay? So if you want to find the impulse, if you want to find the change momentum, if you want to find the impulse, if you want to find the change momentum, if you want to find the impulse, if you want to find the change momentum, those are interchangeable. You can find it several ways. One way to write impulse is to actually write change in momentum. One way is apparently to go force times time. And another way is to go m v final minus v initial. Is that how I wrote it on your formula sheet? I don't think I quite did. This is a 3 equations in one line. We only use 2 of these at a time, but they all equal each other. How did I write it on your formula sheet? It's going to be in the section on momentum there. It's going to be the one right next to the P equals MV. Did I write delta P? And then I wrote equals, because what's final minus initial the same as? Change in. So another way to write this is the delta P, the FT. You can write this as M delta V, because that's change in anything. I tend to use this one the most. Did I write time or did I write change in time? Because time is always technically a change in. This looks really terrifying. It's not. It looks terrifying. I realize that, Courtney. Here's what it's saying. If you want to change an object's momentum, you have to apply a force over a given time. That will make it speed up or slow down, which will change its momentum. And that's kind of Captain Obvious, I hope. You were away, sorry. Logan, that's kind of Captain Obvious, I hope. But that's what this is saying mathematically. But here's what it's also then saying. By the way, if you know how much your momentum changed by, you can figure out how hard you need to push or how long it'll take. Or if you know how hard you pushed and how long you pushed for, you can figure out what your final speed must have been or what your initial speed must have been. There's a lot of information in here. You'll notice this has 1, 2, 3 equations. We only use 2 at a time. So what this is saying is that a force acting for a time will change the amount of motion, the momentum, on a system. So, force times time equals mass times change in velocity equals change in momentum. Doesn't matter which way you write it. Here's really what we're saying. Force times I'm going to stop writing a delta t. I'm just going to write a t. We did that before Christmas too. We said time is always a change in, but we're just going to write a time. One way you can use this is to realize that it's mv final minus mv initial. Can you see where that came from? What did I say at the very beginning of this lesson? What's change in anything? And since I had a delta right there, I said that's going to be v final minus v initial. Oh, are they being multiplied by m? Okay. This is also momentum final minus momentum initial. Or you can say momentum final minus momentum initial equals mv final minus mv initial. That's hidden in there. Or you can say the change in momentum equals force times time. I'm seeing a lot of glazed eyes. Don't panic. This is far easier than it looks. This is actually the start of being able to explain crash test safety. Also, please notice I'm flip-flopping the equations. I could have also written force times time equals change in momentum. Hopefully we're comfortable with, you can put the things on either side of the equation as long as you flip the whole thing. Okay. You may have noticed that I'm paying a lot more attention to my vector notation than in previous lessons. And that's because in momentum questions, there are often changes in direction. And so we need to use precise vector analysis like we did for velocity and acceleration. Let's do an example. A great example of changing an object's momentum is hitting a baseball with a baseball bat. Turn the page. A .144 kilogram baseball is pitched horizontally due east. Due what? Due east at 38 meters per second. After it's hit by the bat, it moves horizontally due west at 55 meters per second. Antonio, what does A want me to find? What's another word for impulse? Change in? How will I write that? Change in momentum. I usually start there. And then I'm either going to use force times time. I'll do that if they give me a force and the time. Or I'll use final minus initial if it's obvious they've given me a final velocity and an initial velocity. Which one am I going to use here? Read the question carefully. What did they give me? See it? I see a final velocity and initial velocity. So I'm going to turn this equation into mv final minus mv initial. Impulse. Evan, you're on your calculator? Sorry? You know, okay. I just saw you type. Okay. Antonio, what's the mass? Yep. What's v final? How did you know that was v final? What word told you that starts with letter A? Yeah, okay, so that's right. Already before Christmas said that part you're going to have to figure out yourself. You use your English sentence sense. Sorry, what did you say it was? Good. Minus, what was M? What was V initial? I can't hear you. Can't be. Can't be. What was V final? 55? Then V initial can't be 38. Yeah? Negative. You just decided when you told me V final was 55, you let West be positive, which is fine. But as soon as you did that, Now vectors are going to make a difference, and we have to be consistent for the rest of the question. Now, you might have decided to let east be positive and west be negative. I'm totally fine with that. We'll all get the same magnitude, and we'll all get the same direction in the end. But since you let west be positive, you know what? I would even then, by the way, here's what I would have done. As soon as I saw east and west, I would have put plus signs and minus signs in front of the velocities, and we'll do that on the next question, okay? But since you let this be positive, we have to make this negative 38. You'll notice you get a minus minus, you're going to get a plus. Anyways, get your calculators out. What's the impulse? .38 meters per second, that's around a 75 mile an hour pitch. So this isn't a major league pitch, but it's probably a good high school pitcher pitch. It's coming in pretty fast. Times 55 minus 0.144 times negative 38. Do you get 13.4? Units. Because change in momentum is still momentum. Impulse is kilogram meters per second. B. Where do you think this impulse came from? And this is meant to be stupidly obvious. I'm looking for a word that begins with letter B, ends in the letter T, and is only 3. Okay. Because one of the things you're going to hear me say later on is change in momentum's got to come from somewhere. Something has to apply a force. Objects don't just change their momentum on their own. Momentum is conserved, is the fancy phrase we'll say. Savannah, what's C asking me to find? What was the average? Yep. Now, at first, we might be tempted to say, well, don't write this down, F equals ma. Do you see meters per second squared anywhere in this question? No. What did they give me in your question? 0.8, this is milli, but what does the S stand for as a unit? They gave me a time. Antonio, what did you find in part A? Savannah, what do they want us to find here? And they gave us time. There isn't perchance an impulse equation that contains a force and a time, is there? Oh, this is another version of the impulse equation. Impulse is also force times time. Change in time. I'm going to stop writing the change in. What did you say they're asking us to find? How would I get the force by itself? By? Yes, thank you. Force is impulse divided by time. By the way, when I told you that Newton's second law was F equals ma, F equals what? I lied. Actually, Newton was much more interested in momentum. This was the equation that he published for force. He had this one, but it's easier to think about it. It does simplify into ma. But for now, we don't have to bother finding the acceleration. We have a nice shortcut because, Antonio, what was your impulse? Loud and proud. I'm going to write 13.4, although I'm going to use my answer button on my calculator. And Savannah, how much time elapsed? Well, it's 0.8. What's milli from your green sheet? 10 to the what? And so it's going to be 0.8 times 10 to the negative 3. I'll probably have to put the bottom in brackets because there's 2 numbers down there. Divided by bracket 0.8 times 10 to the negative 3. $16,740 newtons. I'll go 16,700. What's D want me to find? That's a good question. Sam, what's D want me to find?
Average acceleration.
What did I find in part C?
Average force.
Is there an equation that has force and acceleration in it? F equals what?
Right.
Oh. How do you get the A by itself?
It's about the end.
The force was, I'm going to write 16,700, but I'm going to use my answer button. What was the mass? 0.144? Why did I say average acceleration? I'm not sure the acceleration is constant. I've watched those high-speed slow-motion videos of a baseball being struck by a bat, and I know that the ball actually warps around the bat and then kind of bounces off, and there could be some weirdness going on. I don't know if it's constant, so I'm hedging my bets. And that's also why I said average force, because I don't know if the force is constant. So this is me as a physics nerd just saying, let's assume it is. Well, let's take the average. I get that. 116,000. Is that right? 250? Is that what you got? Yeah. Is that high? Well, I've seen the way baseballs leave a bat. They change their speed pretty quickly. What's the fancy physics word for changing your speed that starts with the letter A? They accelerate pretty quickly, so I'm not creeped out by that. I'll bet you that's okay. Ballpark figure. Ballpark figure. But nothing. Okay. Baseball ball. Nothing. Wow. So I'll go 116,000. Acceleration, what are the units? Sorry? Now, if I wanted to check this, I could also find the acceleration by using the equation that Evan gave us earlier, VF minus VI over T. If I wanted to check, I could go, okay, VF 55 minus VI over bracket 8 times 10 to the negative 3, and I should get the same answer. Wait a minute. Why didn't I get the same answer? Because I made the same sloppy mistake that Antonio made. V final isn't 38 if I let VF be positive. If west is positive, then east is negative. I should have put a negative in there, and now, lo and behold, oh, am I off by a factor of... Did you get 11,625? Oh, it's, you know what? I typed this in wrong. It was 0.8 milliseconds, wasn't it? There's where I'm off. Typo. Same answer. Eventually, if I don't make so many typos. Now, some of you may say, Mr. Dueck, why wouldn't I have just gone VF minus VI over here? I'm so good at that. The nice thing about the impulse equation is in one big Uber equation, it contains F equals ma, it contains VF minus VI over T. It contains so many that often as a shortcut, we can get there in fewer lines than if we did it all systematically by hand. It's a nice shortcut. What's another word for impulse? Change in. When I say change in momentum, what's that the same as? Looking for it to start the letter I. Impulse equals change in momentum. Change in momentum equals impulse. And what's change in anything? Example 2. Who are my football players here? Okay, let's do a little football physics. What's the momentum of a 112 kilogram football player running due north with a speed of 3.6 meters per second? Is this asking me to find a change in momentum? In other words, do you see the phrase change in momentum here? Everybody say no. No. So it is asking me to find an impulse. No. What's it asking me to find? Momentum is what times what? Okay, so for here, I'm going to go momentum is mass times velocity, 112. Velocity is 3.6. What's 112 times 3.6? Yeah, 403.2. I'm going to write all the sig figs here for a reason. So 403.2 units, kilogram, meters per second. Direction, because momentum is a vector. What's B asking me to find? What's another word for impulse? I always start there. So the impulse or the change in momentum is going to be, what's change in anything? Final minus initial. Mr. Dueck, why didn't you write MV final minus MV? Well, I might write that, but the fact that I have a P already calculated here, let's see if I can do this purely with momentums first. What impulse must a tackler impart to the football player to bring him to a? Underline the word stop. What's our final momentum as a number exactly?
0.
That's why I figured I didn't need to go MV final minus MV initial. It's going to be 0 minus, what was our initial momentum? 403.2. And I get negative 403.2 kilogram meters per second north. Or what would be a better way to say negative north? This is again, Carlos, kind of a Captain Obvious moment. It says, if you're running north, the person that wants to tackle you better be hitting you in the opposite direction, which, well, duh, but there's the physics of why. Okay? Suppose the tackle was completed in 0.8 seconds. What average force did the tackler exert on the other player? Okay. Jagger, what does this question want me to find? And I might be tempted to go F equals MA, except what did I just find in part B, Jagger, my friend? Looking for the begins letter. Oh, is there a version of impulse that has force in it? Let's try that first. Impulse equal, what's the version of impulse that has force in it? FT. Jagger, how would I get the F by itself? Yep. So it's going to be 403.2 divided by 0.8. And I get 504 newtons. Direction, if they had asked for it, the same direction as the impulse. And again, pointing at Carlos, my football player, it seems kind of Captain Obvious. Yeah, if I'm running north, they better apply a force south to bring me to a stop. But there's the physics of why. So let's put a little direction just in case they'd asked for it. This is an interesting equation. This is the physics of when a person carrying the football gets blown up. You've heard the expression. If this time got smaller so that you tackled him in a shorter amount of time, if this number gets smaller, what happens to the force of impact? And that's why the biggest collisions are the ones where the guy comes out of nowhere and there's a split second, because you're stuck with the impulse. You have to bring him to a stop no matter what. You've got to cancel out his 403.2 kilogram meters per second. Otherwise, he ain't coming to a stop. You can do it slowly. So if I had made this 1.5 seconds, the runner took a few steps as you dragged him slowly to a stop. That runner's not feeling much of a force. Still coming to a stop. Or if you make the tackle really, really quickly, oh, you must have blown him up. Okay. What if you were only able to apply 300 kilogram meters per second? You slowed the runner down, but he still has some northern momentum to keep going. His mass hasn't changed. I bet you his velocity is slowed down. Although we solved this question using impulse, we really could have solved it using Newton's second law. We could have gone VF equals VI plus AT. VF is 0. VI is, what did I say, 3.6. They gave me the time of point. I could have found A, and then I could have gone F equals what. So why am I bothering with this? Well, The main reason is impulse is the best tool to analyze collisions, which is next lesson. But there are other questions that are more easily understood because of impulse. Consider the following. Example 3. I'm not going to do this demonstration because it's messy. We'll have to use our imagination. Suppose you have two identical eggs and you drop them both from the same height, one onto cement and one into a pail of water. The one that lands in the pail of water survives. Why? That's the question. Well, I know it does. Yeah, let's see if we can do a lovely physics proof. Okay? Let's do a little cement, water, H2O. Dropped. What's VI for both of them? Are they both falling the same height? Yeah, so let's make a little note here. Same distance. So when they reach the end of their destination, I'm not going to say when they hit the ground because one of them's not hitting the ground. When they reach the bottom of their destination, what can you tell me about both of their final velocities? They are also the, gotta be, yes? Okay, so let's make a little note. Same VF. And same mass, because it says identical eggs. We'll assume they're identical. Do they have the same mass? Say yes. Do they have the same V final? Do they have the same V initial? Here's the conclusion I'd like you to write up here. Therefore, the momentum, the change in momentum, the impulse, final minus initial, for the cement egg equals the impulse for the water egg. They both go through the same change in momentum. They both start with the same initial velocity. They both end with the same V final. They both have the same mass. And one way to calculate impulse, way back when, we said was, oh, it's V final minus V initial times M. So that was a big argument, Courtney, to say we're starting out with the same impulse for both of them. Same change in momentum. Is that okay, Court? Yeah. All right. So what I'd like you to write now here where it says discuss your answer, the change in momentum, the impulse of the cement equals the impulse of the water. But what's another way to write impulse? Change in momentum. What's another way that maybe involves forces? It's on your sheet. Look at that 3-in-1 equation. What's another? Loud and proud what? Loud and proud what? Okay. Which one of these has a collision that lasts longer? So here's what's happening. Impulse is also force times time. For the cement, we have such a tiny time, we have a massive force. Yes? For the water, we increase the time, we have a tiny force. That's what seatbelts do. All a seatbelt tries to, because in a car accident, we're stuck with the impulse. What's the final velocity of every car accident ever? Your initial velocity is whatever you're doing on the road. We have to deal with that impulse, and we don't want to have your body experience a big force. The seatbelt allows you to move forward slightly. It lengthens the time of collision, reducing the force. Also, crumple zones on the cars do the same thing. Your bumper and all that, it's trying to lengthen the time of the collision. It's trying to do for you what the water does for the egg. Mr. Dueck needs to pummel someone, but for good physics. I'll pause the video. This idea that I can reduce force by lengthening the time of collision has huge implications. Damage from impulse, from change in momentum, isn't caused by how much momentum is absorbed. It's caused by how fast the change in momentum is absorbed. All of you have gone from 100 kilometers to 0 many times. When? Leaving the freeway, taking off ramp, hitting city street, eventually pulling into driveway. Well, of course, that takes 5 or 10 minutes. That's such a big time. You don't even notice the force that was involved, as opposed to getting hit by a car or coming to a stop in a collision where the time is so small. Same impulse, same change of momentum, but the time is so small it might be terminal. So if any of you do ever get into designing cars for car safety, it's all about, can we lengthen the time of collision, and how cleverly can we do that? And the nice thing about car collisions is the time involved in a car collision is so small, maybe 0.02 seconds. If I can get that to 0.04 seconds, which isn't a big change, I've halved the force. I've doubled our survival rate. If I can get that to like 0.5 seconds, I've massively improved the survival rate. So in some situations, the worst collisions are in some ways the easiest ones to try and mitigate. Here's another way to think about the egg question. Why do they use bales of hay to line some racetracks, especially motorcycle tracks? What's the advantage of being brought to a stop by a bale of hay instead of a brick wall? Well, I can either go through a bale of hay, which has a long amount of time, small force, or I can go into a brick wall, small amount of time, big force. We have a bit of that here in Pitt Meadows. How many of you know who Greg Moore was? Okay, so Greg Moore was a Pitt Meadows grad. He graduated 95, I think, and he was an up-and-comer, one of the up-and-coming leading Formula One racers. And in around 1999 or 2000, he was killed in a race crash. You can find the video. You don't need to. His parents, his dad, I think, owns the car dealership over there. And they changed the logistics because of that crash. They've changed how the walls and cars are designed. But you may notice, if you ever watch auto racing, those cars just seem to fly apart in a car crash. That's deliberate. That's all crumple zones trying to lengthen the time of collision as much as possible. It's not bad design. Wow, that car really crumpled. It doesn't seem very sturdy. No, that's good design. You want that. I used to drive a 1969 Mercury Meteor. I got it given to me. Most of you don't know what a Meteor was. I'll put it in context. Courtney, we fit 39 people into it. So imagine those really big 1960s boats, those massive cars. It was one of those. And that one, I got into a fender bender once. My car wasn't scratched at all, because back then they thought customers wanted cars to be built iron solid, rock solid. Well, where did all the force get transferred to? Me? I was sore. Now we realize, you know what? People would rather have their car get fairly damaged and walk away from the crash. And so that's why modern cars, even in a fairly minor collision, a lot will crumple. In many sports that involve striking something, tennis, baseball, soccer, golf, players are told to follow through when they come in contact with the ball. Why might this help the ball leave with a greater velocity? By following through, which variable are we affecting? And I'll give you the flip side. If you play baseball, when you bunt, why is it that you do that? Or if you play tennis, when you do a drop shot, why is it that you pull back right at impact? What variable are we changing? Time. So if we have the impulse equals force times time, if I increase time, if I've maxed out my force, if I've lifted weights, I can still generate more impulse by following through, by increasing the time that I'm applying that force for. And since impulse is also mass times change in velocity, the mass of the tennis ball doesn't change. Oh, its change in velocity got bigger. Okay. What has more momentum? A 1,000 kilogram car moving at 100 kilometers per hour, or a 2,000 kilogram truck moving at 50 kilometers per hour? I heard somebody whisper maybe already. I thought I heard someone whisper the answer under their breath. No, maybe I didn't. Momentum is what times what? What? They are equal. And I could convert this to meters per second and meters per second if they wanted actual numbers, because we don't do physics with kilometers per hour. But look, if I go that times that, I get the same number. If I go that times that, I get the same number. They are the same, which is why a big truck can be traveling slower in a collision and still apply a fair bit of damage versus a small car would have to be traveling faster. Or it's why, if you've ever watched in the movies, tanks seem to go through everything. They got so much mass, they have so much impulse, not much is slowing them down. Does a moving object have momentum? Sorry? Yeah, because momentum is what times what? Does a moving object have impulse? What's another word for impulse? So this is asking, does a moving object have change in momentum? Why am I going to write Ben? I saw you suddenly go, like you saw it. What? Yeah, if you're at a constant speed, you have no impulse because your momentum isn't changing. So I'm going to put in brackets, must be accelerating. And please, accelerating can also mean slowing down. We're at that point now where we realize acceleration just means changing your velocity. Okay? But if you're at a constant speed, you have no impulse. That's why Star Trek talked about impulse engines. What you were doing was you were changing the speed of the Starship Enterprise. The velocity, I should use the correct term, velocity. When you jump from your lab table to the ground, why do you bend your knees as you land? Or when you're 4 or 5 years old and first going to playgrounds and jumping off stuff, why do you learn very quickly that you need to bend your knees as you land? What variable are we changing? Yeah. Because again, we're stuck with the same impulse. Anytime you jump off of anything, what's your final velocity once you reach the ground? At the end of the impact, always 0. What's your initial velocity? It depends from how high you jumped, but it's that impact velocity. How can we mitigate that? Hey, let's increase the time. It reduces the force. Don't try this because you're all almost adult-sized-ish now, but you may have, when you were a kid, had an experience where you jumped and you didn't flex your knees and you found the force went all the way through your spine and it went through your body. Ow! So don't do that. Which of the following situations is more likely to knock out a boxer? Leaning back while taking a punch? Or leaning in while taking a punch? What variable is leaning in changing? Yeah, it's the time of impact. Okay, so that. Explain your answer. Small force, big time versus big force, small time. Same impulse. And so I hope you're starting to see why, especially in collisions, instead of thinking in terms of VF equals VI plus AT and F equals MA, it's nice to combine them and think force times time equals change in momentum. You can come to some nice conclusions there. Okay. Yeah, your homework's going to be every single question here, okay? Don't lose any momentum in the homework.